Today we're going to be discussing the use of back titrations, sometimes referred to as reverse titrations. So first of all, what are they? A back titration is a titration method where the concentration of an analyte, that is the sample being analysed, whether it be liquid, solid or an aqueous solution, is determined by reacting it with a known amount of excess reagent. The remaining excess reagent is then titrated with another second reagent. Those titration results will be able to show us how much of the excess reagent was used in the first reaction, and therefore the original analyte concentration can then be calculated. So how does this work in simple terms? If you were to walk into a shop with $6 worth of coins and you walked out with $1.60 worth of coins, the rubber duck that you bought must have cost the difference between the original coins that you had and the coins that were remaining at the end of the transaction, which is equivalent to $4.40 that you spent on your rubber duck. In chemical terms, if we were adding acid to an analyte that we wanted to find the concentration of, and we knew that we added 2 moles of acid, we found the acid amount that didn't react with the analyte through titration to be 1.6 moles that was remaining after the original reaction. So therefore the amount used up in the original reaction with that analyte must be 2 minus 1.6. So therefore it's 0.4 moles. So the experimental procedure must focus then on finding out the amount of acid remaining after the initial reaction. All of the other factors can then be calculated from the amount of acid remaining and the other directly recorded data. For example, the mass of the solid that the acid reacted with, the initial molarity and volume of the acid before the reaction. So why would we use back titrations? They're used in an analysis of compounds, particularly those that are insoluble in water, but they are soluble in acid. An excess of the acid is added to that particular solid, and the remaining acid is then titrated against a standard solution of alkali. This allows the acid remaining, and hence the acid used, to be calculated. You need to know the stoichiometry of the reaction, that is the molar ratio between the solid and the acid, which then allows you to determine the number of moles of the solid that was present. Let's look at an example. If we had 150 ml of a 0.2105 mole per litre nitric acid solution and it was added to 1.3415 grams of calcium carbonate, we know that the excess acid was back titrated with 0.1055 mole per litre sodium hydroxide solution, and we know that it required 75.5 ml volume of the base to reach the endpoint. What we're being asked to do is calculate the percentage by mass of calcium carbonate in that sample. So first of all, we need to calculate the number of moles of nitric acid that was initially added to the calcium carbonate. We do that using our N equals CV. So the number of moles of nitric acid will then be equal to 0.2105 by 0.150 litres. That gives us a total moles of 0.031575. We then write an equation for the second reaction, the titration that is, between the nitric acid and the sodium hydroxide. So nitric acid and sodium hydroxide, both aqueous solutions, react to form an aqueous solution of sodium nitrate and liquid water. We calculate the number of moles of sodium hydroxide that was reacted with that nitric acid, and therefore we can find out the moles of nitric acid that reacted. That's our third step. So once again we're using C times V, and this time it's for sodium hydroxide. So the molarity of the solution was 0.1055 by the volume of the solution, which was 0.0755 if we convert that to litres. The number of moles of sodium hydroxide then is equal to 0.0079 ... We save it in our calculator, making sure not to round until the end. Looking at the molar ratio, the number of moles of sodium hydroxide is equal to the number of moles of nitric acid. So it's a 1-to-1 ratio. Therefore, the number of moles of nitric acid is equal to 0.0079 moles. And that is the amount of nitric acid that reacted with the sodium hydroxide. Now we want to have a look at the number of moles of the number of moles of nitric acid, rather, that reacted with the calcium carbonate originally. How would we do that? Looking at the number of moles of nitric acid that reacted, we would have to know the total nitric acid that was added minus the number of moles of nitric acid that remained after that initial reaction. So we would find that by looking at the reaction with the sodium hydroxide. So we input our two values that we've found earlier, which then gives us a value of 0.0236 moles of nitric acid that reacted with the calcium carbonate. Our fifth step then is to write an equation for the reaction between the nitric acid and the calcium carbonate. So we've got a nitric acid solution plus your calcium carbonate, which would be in solid form, gives us calcium nitrate aqueous, and our water, which would be in liquid form, and of course our carbon dioxide gas. We know that the number of moles of nitric acid that reacted with the calcium carbonate is 0.0236 moles. Looking at the molar ratio between nitric acid and calcium carbonate, we know it's a 2-to-1 ratio because we've written a chemically balanced equation. Then we would work out that the number of moles of calcium carbonate is then equal to half of the number of moles of nitric acid that reacted, which gives us a value of 0.0118 moles. So we've already done the equation. Now what we've got to do is calculate the mass of the calcium carbonate that reacted. Since we've worked out the number of moles that reacted, we can then simply times that by the molar mass of calcium carbonate. So you can see that that's what we're doing here. The mass of the calcium carbonate is found to be 1.181. ... We're saving it because we haven't quite calculated the percentage yet, so we're not going to round until we finish off our calculations. So that's the mass of the calcium carbonate that reacted originally with the nitric acid. We've now found that. Our last step, in order to answer the question in its totality, is to calculate the percentage of calcium carbonate. So there we're looking at the mass of calcium carbonate that reacted with the nitric acid being 1.181 ... divided by the mass of the calcium carbonate that was originally added to the nitric acid, or vice versa, which was 1.3415. Of course, for a percentage, we're going to times that by 100. We get a value of 88.076%. And because we look at our significant figures, and the fewest number of significant figures is actually in our volume there of sodium hydroxide, where it's 75.5, gives us 3 significant figures. So we would be rounding that value to 3 significant figures, 88.1%. So that is how you would be completing questions with regard to back or reverse titrations. Now it's time for you to have a go looking at a variety of HSC questions relating to back titrations.